Okay, welcome everybody. Looks like folks are streaming in. I think we have started recording, but welcome everyone to the SMA presentation. The presentation today is on our string inverter solutions that are optimized with ShadeFix and also paired with SunSpec Rapid Shutdown. My name is Mike Mahan. I am one of the technical trainers for the SMA America Solar Academy. With me today is Tyson, also from SMA, as sales contact for this whole territory up in the Northeast. He's available. Both of us will be available also in a happy hour after, right after the close of this session. So if there are follow-up questions, that's maybe a great place to handle them. I will, at the very end of this presentation, kind of shift gears and do a few minutes on the Sunny Boy storage. So that may lead to some more detailed questions, which I think we will push off to the happy hour. But any questions on the ShadeFix or the SunSpec Rapid Shutdown, we should be able to handle, I think, in this session. So feel free to pop messages in the chat queue, and hopefully we can attack them as we're going through on the presentation. I'm going to turn off my video and get into the presentation. The goal of SMA with our Sunny Boy pictured on the left, residential inverter, and our Core 1 commercial inverter pictured on the right, is to provide residential and commercial installers with fully code compliant, very simple to install, lowest cost and highest reliability solutions in all installation scenarios. We'll talk about SunSpec Rapid Shutdown. Many areas of the United States are on 2017 or 2020 NEC, where rapid shutdown really requires something touch each and every module for code compliance. But there are installation scenarios where rapid shutdown isn't required for both the Sunny Boy and the Core 1. Maybe a ground mount for residential, maybe a carport installation for commercial. So we have ShadeFix energy optimization built into our inverters, both the Sunny Boy line and the Core 1 line. And that's what we're going to start talking about. That energy optimization is available whether or not the SunSpec Rapid Shutdown is required. So we'll talk in the SunSpec part about the receiver elements at the array that pair with our inverters for that full code compliance if you're on 2017 or 2020 NEC and need to comply with that installation or rapid shutdown. But you have ShadeFix whether or not the SunSpec Rapid Shutdown receivers are installed, and that's important. So it's energy optimization that is built into the inverter, that is ShadeFix. It does not require any module level power electronics to function. So you're getting the benefit of ShadeFix, the benefit of having module level power conversion devices without having to install them. If rapid shutdown is required, we have simpler devices, the SunSpec Rapid Shutdown receivers, that are very simple, do not work all of the time, so they're higher reliability devices. And for a large commercial install, you may have dozens, if not hundreds, maybe not even 1,000 in a large commercial install. Those devices behind the modules are in the harshest environmental situation of the system. We want them to be as simple as possible, to work as little as possible, so that they will contribute positively to the reliability of the overall system and not be a source of service calls over the lifetime of the system. So we're aiming the pairing of ShadeFix in the inverter and the SunSpec Rapid Shutdown to provide installers the lowest cost, highest reliability, highest yield system that is always code compliant to the level needed for each and every install. Two slides here. One is a very quick overview on the Sunny Boy line, one a very quick overview on the Core 1 line, just to point out the features that squeeze the most benefit out of the ShadeFix optimization in each of these inverter lines. The Sunny Boy US-41 is our residential Sunny Boy line with the SunSpec certified rapid shutdown transmitter built into it. There are 6 power classes as shown at the top. There are multiple input tracking channels in all power classes. The 2 smaller have 2 independent inputs, and the 4 bigger have 3 independent inputs. The Sunny Boy is handling each of those independent inputs, just like the name says, independently. The voltage operating range for each of those inputs is 100 up to 550 volts DC. Each of the inputs can be working at different voltage points as long as they're within that window. So there's a lot of design flexibility for different string length, different orientations coming into the inverter. but that wide voltage window also will unlock maximum benefit for ShadeFix, and we'll show that later. Similarly, if you're not familiar with the Core 1, the Core 1 US-41 line has a SunSpec certified rapid shutdown transmitter built into it. There are 3 power classes for the Core 1 US-41 line. All of them have 12 string inputs on each inverter, and that is broken down into 6 independent tracking channels with 2 string inputs on each of those input channels. The operating voltage range for each of the channels is 150 up to 1000 volts DC. So a huge range for lots of flexibility, different string lengths, different orientations, whatever the need may be. But that wide voltage range will also squeeze out maximum benefit from the ShadeFix optimization built into the inverter. So that's kind of the important bit to know about these 2 products. Lots of independent tracking channels with really wide DC voltage ranges for each one of them. Before we get into the technical, gory details of what ShadeFix is doing, what the actual optimization is providing, I have 2 very high-level slides. So these are intended to kind of be a discussion points potentially with system owners. So out in industry publications, you may have seen something like what I'm circling in red in these 2 graphics, that a string inverter system may be quote unquote only capable of working at the point of the weakest module. And what ShadeFix is providing at a very high level is preventing those statements from ever being true. Without the need of module level power conversion electronics, with or without shade, it can prevent the system from being trapped at the point of the quote unquote weakest module. So that's kind of a very high level view of what it's doing, the benefit it is providing. And also another high level graphic, and this is coming from the white paper on ShadeFix that we have posted on the SMA-America.com website. This graphic is contrasting the SMA ShadeFix optimized inverters to the standard DC optimizer system. And the graphics along the bottom are showing that the ShadeFix optimized inverter can outperform, that is, produce higher yield. And what that is AC kilowatt hours out of the inverter, because that is the only thing that spins the meter backwards. That is the only thing that provides the system owner benefit. DC watts off of a module at any point in time does nothing for the system owner if it does not increase the number of AC kilowatt hours out of the inverter. So the graphic at the bottom is showing that the ShadeFix system can outperform, that is higher yield, higher AC kilowatt hours out of the system in the vast majority of shade scenarios. And the comeback question would be, of course, well, why? How can it do that? And we're going to have a graphic kind of showing in a little more detail at the close of the ShadeFix presentation. But the important thing for someone who may not be super savvy in the industry to understand is those DC optimizers behind each and every module, because of the architecture of the string inverter paired with them, those DC optimizers will be having to boost or buck their module voltage and thus consume DC watts, whether or not they are providing a shade or mismatch benefit. That continuous power draw reduces the AC kilowatt hours out of the system in the vast majority of shade scenarios, only when there is such severe shade that having those devices provide that mismatch benefit, that finally outweighs their continuous power draw. And we'll again show a graphic that explains it a little more detail at the close of the situation. But the important thing to understand and convey to a potential system owner who's weighing ShadeFix against the standard DC optimizer system is those DC optimizers are consuming DC watts all of the time the system's in operation. Generally, it's just pitched that they provide the ability to squeeze a few more DC watts off of a module in a certain shade scenario, but the fact that they're consuming DC watts all the time, whether or not they provide benefit, is usually swept under the rug. So again, this graphic, I think, is a great talking point for a discussion with a potential system owner, but we're here today to talk about the gory details of what ShadeFix is doing. So the next 4 or 5 slides is covering all of that. So let's dive into it. Before we get there, I want to talk about the graphs that we will use to discuss the finer points of what the optimization is doing. So what we're looking at is a string of PV modules. I'm assuming these modules are all the same type from the same manufacturer. They're connected in series. This string of modules is experiencing the same temperature and same irradiance. So we have a nice uniform string of PV modules. Any PV device is going to have some current versus voltage curve like shown in blue. So we have the vertical axis current in amps against DC voltage, the horizontal axis here. We have this blue curve, the current versus voltage curve. So for this hypothetical string of modules, uniform conditions, we have a nice smooth curve. And generally, I find it very hard to pick out from the IV curve, the blue curve reference to the left vertical axis, where the maximum power point is, that is the DC voltage where it occurs. The red curve is the corresponding power versus DC voltage curve for this string of modules at this given point. So we're multiplying the current by the voltage. We're using the right vertical axis with units of watts to graph that power versus the same DC voltage curve. On that graph, it is very easy to see the DC voltage where the maximum power occurs, and also to read off actually what that maximum power is. So we'll show both the red and the blue curve on corresponding slides, but I want to let everyone know what these are, why we're going to be using them. Another important thing to understand for the discussions to follow: the shape of the blue curve and the shape of the red curve are completely set by the array, by the module type we've chosen, in this case, how many we have in series, and the environmental conditions they're experiencing at this point. There is absolutely nothing the inverter can do to change the shape of these curves. And that discussion is true for a string inverter, for a microinverter. This is all what the module is experiencing. Obviously, each microinverter would be dealing with its own module. They'd be slightly different shape of these curves. But again, the shape of the curves is dictated by the PV device and the environmental conditions it's experiencing. There is nothing the inverter can do to change the shape of these curves. But the inverter is the DC load connected to this array. It is capable of choosing the operating point of the system. That is the DC voltage point where the system operates. So the inverter cannot change the shape of the curve. And if we look at the red power versus voltage curve, for that particular set of environmental conditions for this array, the system has to work at some point along the curve. And as the DC voltage changes, obviously the power level will change. So the shape of the curve cannot be changed by the inverter, but it is 100% up to the inverter to choose the DC voltage operating point for which the system will be operating. So it can shift the system along the curve, even though it can't change the shape of the curve. Maybe it's beginning to become apparent why having a very wide voltage operating window would be beneficial. Having more range for that choice of DC voltages will be very beneficial for the case where we have this nice smooth power versus voltage curve. And as we get into the discussion of what ShadeFix is doing, having that wide range will maximize the benefit of ShadeFix. So very, very useful to have that very wide voltage operating range. So let's now, before we get into the discussion of what happens in shade scenarios, one last thing to talk about. We mentioned that ShadeFix does not require any module level power electronics, so power conversion electronics at the array, but it is going to make use of devices that are built into the junction box of PV modules, the bypass diodes. So generally, you're probably familiar with these devices. Most commercially available silicon PV modules will have probably 3 bypass diodes built into the junction box, that black plastic thing on the back side of the module. Those bypass diodes are wired in parallel with groups of cells in the module. So generally, each bypass diode will be wired in parallel with 1/3 of the cells in the module. And what they are providing is a safety valve path for current to flow in conditions when the modules, or sorry, the cells they're wired in parallel with begin to act as a high resistance. That could be hard shade, it could be some physical damage in the wiring path here. Whatever the case may be, they are providing a safety valve for current. So if they are a lower resistance path for current to flow, current can avoid having to be forced into that high resistance path and can flow around that high resistance path. And all of the current from the remaining cells in this module and all the other modules wired in series can flow across that bypass diode. it's important to understand that the section of cells that are in parallel with this bypass diode in this situation would not contribute voltage, but this section is also not acting as a block for current flow. So those are put in parallel with these PV cells to prevent the series electrical wiring single point of failure issue. So these are provided with commercially available PV modules. There's nothing that needs to be added to the system. They will be utilized, but they're not extra equipment. So if you look at a PV module, we have here, I think, 72 cells. You'll have 3 bypass diodes in this hypothetical situation, protecting 24 cells. In uniform conditions, no shade, the current is flowing through all of these cells. They're all contributing voltage. Current is coming into this module, flowing out to its nearest neighbor. In situations where there's shade on some portion of the module, we're showing shade on a section protected by 1 bypass diode. Now, if these shaded cells are acting as a high resistance, current will simply, instead of trying to force its way into this column of these two columns, will flow across the bypass diode as the path of lower resistance and then flow out of the module. So we're not getting voltage contribution from this section, but we're not restricting current that is flowing through all of the rest of this module and all of the other modules wired in series. So let's come back to the current versus voltage and power versus voltage graphs and start to begin deconstructing this weakest module in the string myth for hard shade scenarios and also partial shade scenarios. So we're back to the uniform environmental conditions. So uniform light levels and temperatures across this hypothetical string of modules. We have a little speedometer view of power here below each module. They're all capable of working at the same power level. We've reconstructed that smooth blue curve and the smooth red curve. Again, it's completely on the inverter where, that is, what DC voltage to operate this system at. Generally, a string inverter wired up to these guys. When it wakes up in the morning, it's going to be at open circuit voltage. It's not loading the array. You'll be out here wherever VOC is. As it sees that there's enough voltage to productively make power from the string, generally it will drop voltage, maybe 85% of VOC. Let's say it's on the shoulder of this curve here, and it will begin adjusting the DC voltage for the system down and up. And as it's doing that, it's going to look at power. And it's going to just climb this hill. When it gets to the top, where this maximum power point is for these conditions, it will continue to push slightly lower and higher. Because as the light levels and temperatures change on the system, the shape of these curves will change. So they'll move around all day, every day. So that algorithm's always there, pushing slightly lower and higher on voltage. And so it will stay at the top of this curve all day, every day, very effectively, very efficiently, as long as there is only one maximum point on this curve. It is a very straightforward, simple, and highly effective algorithm. So the inverter will do that little dance, tracking the maximum power point. What happens now as this array that's attached to it begins to be subjected to shade? So let's first look at a situation of hard shade and see what happens with this weakest module in the string myth. So now we're going to take one of these modules and shade with hard shade. Let's say it's me climbing on the roof with cardboard. I'm going to slap cardboard on one of these modules so that all of the bypass diodes in this module activate. If there is no current flow through any part of the cell, it's not contributing any power. If the weakest module in the string myth were true, this whole string would have to work at the point of the weakest module, which is 0 watts. That's not what is going to happen. When you look at the IV curve and the power versus voltage curve for this scenario, we've in essence carved one module out of the string. So the curves will stop at a lower DC voltage. You're taking off pretty much the VOC of one whole module because we've shortened the string. But all of the remaining modules are uniform, that is, in terms of light level and temperature. So you have a smooth IV curve and also a smooth power versus voltage curve. Yes, the maximum power voltage has shifted lower and the available power has shifted lower because we've lost the contribution here. But it's very easy, even for a non-ShadeFix optimized inverter, to find this maximum power point, which is well above 0, and stay there. So it's very easy in the hard shade scenario to disprove this weakest module in the string myth. Most people would, however, come back and say, well, that's not the only case we're considering. What about the case where you have partial shade on this string, where you have modules capable of, they're unshaded, capable of working at high power, and you have partial shade where you can get power off some modules, but not the same level. So let's look at that case. We're considering partial shade on, in this scenario, 2 modules of this string. If we then think about what the IV and the power versus voltage curves look like as we build this string from the left to the right, all looks as before until we go from this 4th module and try to add this 5th, the first in this graphic, partially shaded module. At that point, if we want this PV module to contribute voltage, that is to continue drawing the curve out to the right to higher DC voltage, if we want it to contribute voltage, current has to flow through this module. And all of these devices are wired in series. So there is one value of string current for the string. So if we want current to flow through this module, it's receiving less light. It can produce less current than the unshaded modules. So for it to contribute voltage to the string, that means that the current has to go down. So if we want to go out to the right on this graph, we have to work at a lower voltage for this, lower current for the system. So now if we look at what's happening to the curve, we have humps in a very technical term. If we move out to higher DC voltage, we are restricting the string current to this lower value. So we have humps on the blue curve. And what happens to the red curve? Well, we also have humps on that curve. And if we look at this scenario, we have 2 points that I've labeled 1 and 2, where in a narrow DC voltage range, if we move from point 1 or point 2, lower or higher in DC voltage, power is going down. So if the system were working at point 2 with no ShadeFix, it would do its normal dance, push DC voltage a little lower, power goes down, would come back, push DC voltage a little higher, power goes down. So it would stay working at point 2 because in a narrow voltage range, that is the maximum power point. But in this partial shade scenario, there are multiple choices on the curve for maximum power point, and point 1 has higher overall power. So this is what ShadeFix is preventing, being stuck at point 2. And what ShadeFix is again, is optimization built into the Sunny Boy line and the Core 1 line. It is working on each of the independent input channels at different intervals. It's acting like those are independent inverters. So it's performing the optimization on each of the inputs independently. And what it does, and by default, the sweep period, that is the frequency at which the ShadeFix optimization sweep occurs, is set to be every 6 minutes or 360 seconds. And the sweep takes about 1/10 of a second. So every 1/3600th of a production period, the inverter will say, okay, well, I know I'm on at least a local maximum point with my standard algorithm. I'm going to sweep down in DC voltage to my minimum operating voltage. I'm going to come back and go up to VOC and finish the sweep where I started. During the sweep, it is tracking power. So it is logging the power that is being produced at all these DC voltages. And when it finishes the sweep, if it sees any point like point 1, it will simply move there after the sweep is completed. So it's not doing this all of the time. We said that this was 1/3600th of every production period. So in essence, 1 second of every hour the system is producing, this sweep is being performed. So this is the safety check to say, okay, well, I don't know how fast the shade is coming in. I'm going to check periodically to make sure that we're not being impacted by partial shade and that some point like point 1 is being created that I didn't track to. So you have this periodic sweep function to ensure the system, even in conditions of partial shade, is working at the highest possible power point for the system. Again, requires no module level power conversion electronics to perform. And you get all of this in the inverter. So when we get to the rapid shutdown discussion, remember that the ShadeFix's optimization is available whether or not there are rapid shutdown receivers behind these modules. So this is what ShadeFix is doing in very technical terms. And again, it's preventing the system from being caught, quote, at the point of the weakest module here. So the sweep, again, will cover the whole DC operating voltage range of the inverter. And the sweep doesn't care how many of these quote unquote humps there may be. So there could be multiple shade impacts on this string, as long as this optimal point here is within the very wide voltage operating range of that input channel on the inverter, the algorithm will find it and move there and work there. So this inverter-based periodic sweep function is providing that benefit of making sure that partial shade is not dragging down the whole system. Before we talk about the standard DC optimizer system, the savvy viewer will say, okay, well, wait a second, Mike. You said you're moving from this higher voltage, lower current point back to this lower voltage, higher current point because there's more overall power from the string. But aren't you, because you're working at a lower voltage, aren't you then sacrificing potential contribution from these two partially shaded modules? And the savvy viewer is absolutely correct. We are moving back to lower voltage, higher current, which is then going to force the bypass diodes of these modules to activate. So they're not contributing voltage. They're not restricting current, but they're not contributing voltage. So the savvy viewer might say, well, isn't a DC optimizer system going to be able to squeeze some DC watts off of these two modules in this partially shaded scenario? And the answer is yes. But again, the takeaway is that DC watts off of a module in a shade scenario is not what makes the system owner benefit. It is only AC kilowatt hours out of the inverter that matters. So your point or your question, follow-up question would be, well, then again, how can you go back to that first graph? How can you say the ShadeFix system can outperform? It is because of the behavior of the DC optimizers in all of the other points of time when there are not shade or mismatch events affecting the module they're attached to. The standard DC optimizer system, the string inverter for that system expects a constant input voltage, independent of the modules being used, independent of the string length coming to it, independent of the time of day or time of year, so the environmental conditions of the array. For a short string, what that means is since this guy is expecting constant voltage, the DC optimizers behind each module likely will be having to boost voltage to have that, to achieve that constant string input, voltage input that the string inverter in this system is expecting. For a long string, it would be the opposite. They'd have to be pushing voltage down. These devices obviously do not work for free. They are consuming DC watts to perform this boost or buck function. So all of these devices are consuming DC watts, thus reducing the AC kilowatt hours out of the inverter for no shade or mismatch benefit. If we look at the hard shade scenario that we looked at before, if that module is completely hard shaded, the DC optimizer has no voltage coming to it, it's going to be off. Either you get no voltage contribution or you get the natural voltage out of, well, let's just say we get no voltage contribution. The string voltage in the string inverter is expected to still be constant. All of the remaining devices have to make up the slack. They have to boost their voltage, their module's output voltage even higher. In the partial shade scenario, you can calculate the available power out of this string, divide that by the constant string voltage the inverter here expects, and get a string current. If the partially shaded modules can't work at that string current, it's above where they can work, then the optimizers attached to those partially shaded modules now actually have to push voltage down to boost output current to be in line with what is required. That means all of the remaining devices have to work even harder because now you have two devices that are pushing voltage down really the wrong direction. So these devices, there is an impact of what one of these devices does on the others, and they will really always be boosting or bucking module voltage all of the time the system is in operation, consuming DC watts. So the fact that a couple modules might be providing more DC watts in this scenario, the vast majority of the time, all of these devices are consuming DC watts. So unless you have really, really, really severe shade, then essential continuous vampire draw of all these devices will outweigh the benefit they may provide in certain shade scenarios. So that is really the underlying reason for that graphic that we started this conversation with. The construction of this system requiring that constant string voltage means that these devices will be boosting or bucking module voltage all the time the system's in operation, consuming DC watts, robbing the true value, that is AC kilowatt hours out of the system from the system owner. And again, the important bit, the question that it's AC kilowatt hours that matters, not DC watts off of any module in any given scenario. You know, that's the takeaway, but it is not just the SMA Academy that is saying this. We had a year-long study that was performed by an associate professor at the University of Southern Denmark, who over a year's period of time compared the behavior of three identical systems, identical arrays, identical DC capacity, identical AC capacities out of the 3 inverters, one of which was an SMA ShadeFix optimized inverter, and the other 2 were standard DC optimizer systems. Over the year, for many weeks, he would have the systems just be experiencing environmental shading, with clouds coming in. For several weeks, he put artificial shade objects in front of all 3, so a giant pole in front of all 3 arrays, so there would be a close-by shade object sweeping across them during the day. So you had a shade object as well as environmental shading. For several weeks, he had a cotton cloth across one module in each array so that you had artificial mismatch on the array. And over the whole year, including all of the shade scenarios, he has energy meters calculating the AC kilowatt hours, and the ShadeFix optimized system produced more AC kilowatt hours over the whole year, including all of the shade study periods, than either of the DC optimizer systems. One would expect on sunny days with no close-by shade objects that the system with the highest efficiency would produce the most AC kilowatt hours. Even though the SMA ShadeFix system on paper didn't have the highest stated efficiency, the author found that it produced the most AC kilowatt hours. Also, you had no nearby shading objects, but you had environmental shading. They found that the ShadeFix optimized system generally produced more AC kilowatt hours. In fact, really the one time that he found that the DC optimizers did outperform was when there was generally good irradiance, but rapid swings. So bright sunlight, but very, very rapid cloud movement. So if we look at the actual data from the paper, if you look at the comparison, so this is a comparison on a particular day. So you have the 3 systems, and the modern string inverter is the SMA ShadeFix system. He has this graph, their production, and they were fairly small systems. And so this is decent production. So it was cloudy until about noon. Then you can see there's swings in the irradiance, and then it gets kind of cloudy again. And over the whole day, ShadeFix produced more, but you can see fairly similar behavior. On the sunny days, you can see that modern string inverter actually, it's actually clearly above the other curves. It produced more. And these are very kind of low production numbers. So on cloudy, overcast days, we have swings here, ShadeFix produced more. It was only on days where there was good production and exceedingly rapid swings in irradiance where the module level systems outperformed, and not by a very large margin. And this actually caused some SMA engineers to kind of rethink the minimum sweep period for our ShadeFix. We thought if this is the only time that the optimizer systems could outperform, maybe we should lower the minimum sweep time of ShadeFix and be able to attack scenarios like this and outperform it in all scenarios. So when we, for our Sunny Boy line, we had 6 minutes being the minimum sweep time. We've actually lowered that down now. I think you can lower it down to 3 minutes. The default is still higher than that, but you actually can lower that sweep period down. The maximum sweep period is up to 30 minutes. So kind of the thought being we didn't want to be chasing clouds, but maybe there are some levels of rapid irradiance, some scenarios where somebody would want to reduce that sweep period down below the 6 minutes. One other thing that's important is looking at this ground mount system, you can see the picture of the artificial shade objects that were introduced for part of this year-long study period. If you take those away, if you have a nice ground mount system where you have clear cut any vegetation close by the array back, you believe that over the 20-year lifetime of the period, of the operating period of the PV system, that there will not be any non-uniform shade. Any soiling will be uniform, that there would be no benefit to having the ShadeFix sweep. It can actually be deactivated. If you don't believe it's going to provide any benefit, why spend any time doing the sweep? So it's possible to even turn it off if that is desired. But generally having it on as a safety function for trees that grow over time, maybe neighbors build a house nearby, things like that. Generally recommended to leave it activated. But this data, these curves from the actual study paper are not included in the white paper we have on the SMA website. We have distilled it down more to that graphic of the 4 different shade scenarios, comparing the ShadeFix yield to a standard DC optimizer system. We feel that's a far better discussion with a potential system owner on the benefits, very easy to understand of why the ShadeFix can provide higher yield. But I think for this level of discussion, having these graphs is very useful. So interesting to look at a lot of the real world data. Changing gears a little bit. We did mention that many areas of the United States are on 2017 or 2020 code. And so the vast majority of residential or commercial PV installs might be subject to rapid shutdown requirements. And for 2017 or 2020 code, that really currently requires something touching each and every module to be able to achieve the voltage levels required once rapid shutdown is triggered. So to be able to provide a simple to install and very user-friendly method of full code compliance, what we've done is both the Sunnyboy US-41 lines and the Core 1 US-41 lines, the ones that have ShadeFix built into them, we have also incorporated into those inverters a SunSpec certified rapid shutdown transmitter. If you're not familiar with SunSpec, it is an industry organization that has many member companies, I believe over 100 now, of which SMA is one. And they tackle industry-wide problems. Rapid shutdown obviously affects most vendors in the PV space in the United States. So they published an open standard for a power line communication signaling protocol that could achieve all of the requirements of 2017 or 2020 rapid shutdown. They certify equipment to be in compliance with their published open standard. So they have certified that the transmitters in our Core 1 and Sunnyboy lines are compliant with that open standard power line communication protocol. And those boards are responsible for generating that communication signal when the board is turned on. The other part of the puzzle for compliance is receiver elements certified by SunSpec at the array that are listening for that signal. And it is in essence a keep alive signal or permission to operate. Whenever it's present, these receivers are tasked with allowing their modules to participate in the string they are part of, but at the point that the inverter under ShadeFix commands, they are not doing any boosting or bucking of DC voltage. They are not converting DC current to AC current. They are acting simply as module on-off switches. So far less complex circuitry, and all they are doing for the most part is listening for this signal. When this signal disappears, very quickly these devices have to acknowledge that, and then they will isolate the modules that are connected to them from the string they are part of. They won't break the string, but they will go down to a very low, safe off voltage, such that even a long string will meet all of the requirements in terms of voltage that are asked by 2017 or 2020 rapid shutdown code. The SunSpec organization has on their website a list of SunSpec certified rapid shutdown receivers, but anyone who is considering using an SMA SunSpec certified inverter, we strongly request that you use only devices that are on the SMA approved or SMA compatible list of SunSpec certified rapid shutdown receivers. The SunSpec certification takes care of making sure all of the power line communication signaling for rapid shutdown occurs as it should. But there are many other operational and safety functions that are going on at the same time in our inverters. And so the SMA compatibility testing tests all those other functions in conjunction with the rapid shutdown signaling. So please, there is a list linked off of one of the banner images on the SMA-America.com website that has this compatibility list. So it is updated fairly regularly as SunSpec is certifying devices. For receivers, we are going through compatibility testing and expanding this list. For the Sunnyboy line, there are currently 3 devices, SunSpec certified receiver elements that SMA has also approved for use with the Sunnyboy line. There's a device that SMA sells as an SMA part, even though we don't make it, called the JMS-F, and 2 devices from a company called AP Smart, their single module device, the RSD-S-PLC, and their dual module input device, the RSD-D. So all 3 of these are approved for use with the Sunnyboy line. And for the Core 1 line, the single module device from AP Smart has gone through that compatibility testing. We're currently going through the RSD-D device compatibility testing, but have not completed it yet. So for the Core 1, it's the JMS-F and the RSD-S-PLC device that are on that approved list. Again, that's clearly shown in the document on our website as well as the product page for the SunSpec shutdown receivers linked off of our homepage as well. So again, strongly request that folks use only devices with our inverters that have gone through this compatibility testing, because again, we're testing way more than just the SunSpec signaling that is done with the certification by SunSpec. And please note that devices that are not certified by SunSpec will never go through the SMA compatibility testing. Devices like the TS4-A-F from Tigo may be labeled as SunSpec compatible, but they are not certified by SunSpec, so they will not be on the approved list for use with our Sunny Boy and Core 1 devices. So please, please, please use only devices that have the green check mark, in essence, in this table when paired with our inverters with the SunSpec certified rapid shutdown transmitter built into them. And anyone at SMA, again, if you have trouble finding it on the homepage, we'll be happy to provide the link to that document or provide the document directly. So these devices, again, only when rapid shutdown is required, these devices are paired with their modules at the array, and the inverter's SunSpec transmitter is turned on during commissioning. Very simple for installation. These devices are acting only as module on-off switches, so they're not sending module data back to the inverters. So during commissioning, you do not have to wait for all of the devices to be detected and to report back. There is string and input channel level monitoring available on the inverters, but there is not module level device coming back from these guys. And again, they are very, very simple devices acting as that module on-off switch. They do not need circuitry to boost or buck module voltage, and they are not working all of the time to do that while the system's in operation. They are there for the minimal amount of complexity required for full code compliance. And again, if rapid shutdown does not apply to an installation you're using the Sunny Boy or the Core 1 for, you simply don't procure these devices. You still have the ShadeFix optimization in these inverters, and you just don't have to turn on the rapid shutdown transmitter. As simple as that, being able to perfectly tailor the complexity of the system to the code requirements at hand. Okay, let me see in the chat window. That looks like a reply from Tyson. I don't know if there are any questions, Tyson, that should be handled before a quick few-minute overview on the SMA Sunny Boy storage. When we set up this session, we got some feedback that there may be some questions or interest in the SMA Sunny Boy storage AC coupled residential battery inverter. So while this is completely separate topic from the ShadeFix and shutdown that we just talked about, we thought it worthwhile to at least have a few minutes opening the discussion for the Sunny Boy storage. And if there are more in-depth questions, Tyson and I would be very happy to take those in the open networking session that will start at the close of this session. But I wanted to provide a little upfront information and also notification for folks who are familiar with the Sunny Boy storage of a new battery from BYD that has just been added to the approved list for the Sunny Boy storage. So the Sunny Boy storage, while this picture, if you're not familiar with the device, may look like the Sunny Boy PV inverter we just showed, the Sunny Boy storage is a battery inverter only. So this would be an AC coupled storage device that could be added to a home with or without PV. It connects to 1, 2, or 3 high voltage batteries on the approved list. So we have our 10 kilowatt hour BYD shown in the picture on the left in column 2, and the new BYD battery that can scale from 20 to 32 kilowatt hours per device. So again, 3 of the 32 kilowatt hour batteries connected to the Sunny Boy storage would provide 96 kilowatt hours of storage for this system. The Sunny Boy storage AC output power limit is either 5 or 6 kilowatts. There are 2 models. You pick which power limit you'd like. And again, then you attach batteries to scale the storage, the, in essence, electron tank behind this device. And most folks that we discuss this product with, the Sunny Boy storage with 1, 2, or 3 batteries, AC coupled into a home service panel. This is a grid interactive inverter. Without this device in column 3, when the grid fails, goes away, this device will stop exporting power just like our Sunny Boy PV inverter would. So most folks want the extra equipment to have the system be able to create a microgrid should the utility grid fail. And that's what the automatic backup unit is. It has several components in it. It's not very exciting looking, but it has all required equipment to allow the Sunny Boy storage to safely be a grid former and provide battery power for loads and potentially allow a PV inverter to stay online during a grid failure. So this device is, I think we commonly consider it required equipment. It's not technically, but most people, the use case, they want this device to be able to create a backup microgrid in the case of a grid outage, and the automatic backup is required for that. But the new BYD battery, the footprint is really kind of the same as the old one. It's just each brick, as you build this battery, you're actually just stacking these storage bricks together, very simple to install. They are now 4 kilowatt hours versus the old version. It was roughly 2.5 kilowatt hours per stack, and it goes to a higher stack. So they go up to 32 kilowatt hours per battery. And again, up to 3 can be attached to each Sunny Boy storage inverter for a pretty hefty amount of backup energy there. The automatic backup unit, it has a control board that it has a 200 amp isolation contactor in it to isolate from a faulted grid, a control board to tell the Sunny Boy storage that it is safe to form a backup microgrid. And there are also 2 50 amp breakers provided in the ABU directly for landing the AC conductors of a Sunny Boy storage and the AC output conductors of a PV inverter, potentially a Sunny Boy, directly in the ABU. So quite often this is used between utility service and the main home panel, and then you have the ability to land those inverter outputs directly in the ABU. They could be landed in the main panel if needed, but we're providing those spaces directly in the ABU. And there is also a 5 kVA autoformer for load balancing when the system is working in backup mode. It's important to note, some folks, I think the 50 amp breaker, these are big enough to handle the largest capacity Sunny Boy and Sunny Boy storage we have. Just be clear to potential homeowners that because there's a 50 amp breaker does not necessarily mean these devices will be providing 50 amps of current in operation, but we wanted them to be beefy enough to handle the sizes, the max sizes that we could wire up to them with SMA equipment. And again, there's a 200 amp contactor provided in the device, and so could work very nicely between the utility service and a main panel rated at 200 amps. So kind of as a backup for a, between utility service meter and the main panel if desired. And just to give you an idea of kind of what we talked about the Sunny Boy, to give you an idea of the Sunny Boy storage and the ABU in real world installation, the gray lid is the Sunny Boy PV inverter, the more white lid is the Sunny Boy storage battery inverter, and this box to the right of the Sunny Boy in this picture is the ABU. So we have in this situation, Sunny Boy storage, Sunny Boy ABU, as we do in these 2 pictures. And then here we have Sunny Boy storage. You can see the ABU to the left, and to the right are 3 of the 10 kilowatt hour BYD batteries. So now one of the newer BYD HVL batteries at full height could be 32 kilowatt hours and really take the place of all 3 of these batteries. So very, very, a very nice improvement, I think, on the storage capacity of those BYD batteries. Like I said, this has been a very general overview of the functionality, but if you have follow-up questions, myself or Tyson would be happy to address those in the happy hour session that's going to start in about 10 minutes. Before I open up the floor to questions, I want to make sure everyone is aware of a new standalone app that SMA launched not that long ago called the Energy app. This is a free app for Android or iOS devices to provide visibility to any SMA system registered to our Sunny portal. So this will not take the place of the Sunny portal websites, but it can be used to view systems that are registered to the Sunny portal. And for a system with a Sunny Boy and a Sunny Boy storage, you see what the visualization of the system would look like. I think it's a very nice modern view with, in this scenario, we have a PV inverter, we have a Sunny Boy storage. In the ABU, there is an energy meter. So there's also information on home usage and net flow to or from the utility grid. So quite a bit of information, but I think a very modernized look and feel to what our old standalone Sunny portal app used to show. So the Energy app I think used in conjunction with Sunny Portal is a very useful tool, generally meant for system owners to monitor their systems rather than installers to manage their fleet. Generally, the Sunny Portal website will probably be more useful for that, but it certainly can be used. If you have an account with multiple plants, you can sort through those plants on the Energy app as well. But I think a very useful and modernized graphical presentation of system behavior for, again, primarily the system owner benefit, but also the installers for lots of plants. But I want to make sure everyone's aware of that. Again, free app for Android or iOS operating systems. And again, is viewing plants that have been registered on the Sunny Portal. So it is not a standalone website from SMA that systems need to be registered. It's a visualization of systems registered on the Sunny Portal. Okay, that's a lot of Mike talking. I don't know if there are questions that Tyson has not answered in the Q&A as well, but
indeed there was one, Mike. Great job as always. But Peter Diamond asked a question, and there was another person who was trying to get at how are we kind of addressing the DC watts consumption, or perhaps we could rephrase it as penalty of the optimizers. I'm not sure if you're able to find that question in the Q&A, but is that something that you might be able to elaborate on a little bit?
So a couple ways. I mean,
please explain how an optimizer consumes DC watts, or would we say it cancels or clips DC watt production?
Oh, okay. So that is a great question. And yeah, so I would say that the way I would express it, I would use the term clipping only if the power processing limit of the optimizer is below what the PV module attached to it could provide. And that is not what I was intending to express on any of the graphs on this page. I was trying to emphasize that you have a power conversion electronics device in that DC optimizer. It can't work for free. It is being powered by the PV module attached to it, and it is being asked to do something. Because of the construction of the standard DC optimizer system, where the string inverter expects a constant string voltage, like I said, independent of how long that string is, where it's installed, and what environmental conditions it's facing, that architecture means that it's up to the DC optimizers behind each and every module to make sure that string voltage is constant. So for a short string, these devices will very likely have to be boosting. The module voltage won't be high enough that the string voltage naturally meets that expectation of the string inverter, that they have to boost that output voltage so that the string voltage is that constant expectation. For a long string, it would be the reverse. You'd have a natural string voltage that would be above potentially what the inverter expects. They would have to be pushing voltage down. So they are boosting or bucking module voltage. They are performing a power conversion step that does require power to do. So they are consuming DC watts off their module to do the boost or buck function that is being required of them by the architecture of the system. So I would say that's a power draw for their operation. And I would distinguish that potentially from clipping. And again, every second this system is in operation, these devices will have to do that, whether or not there is shade on their modules. It's all a dance because this inverter was architected to be a very simple device that converts DC current to AC current at a constant input voltage, the highest conversion efficiency for the inverter, which sounds good, but the consequence of that architecture choice is that the optimizers have to be boosting or bucking voltage really all of the time the system's in operation, whether or not they're providing a shade or mismatch benefit. And again, it's only AC kilowatt hours out of the inverter that will make the system owner benefit. So the focus on squeezing a few more DC watts off of a particular module in a certain shade scenario dismisses the loss of DC power by each and every DC optimizer in the system all of the time the system is in operation. So I don't know if that completely answers the question, but I do want to draw the distinction between clipping and the continuous power draw in operation.
And they're also generating heat while they're doing that, which, you know, with an IR or thermography, you can see that, and that's the enemy of PV module production, right?
Yep.
Mike, I don't know if we lost your audio there.
Can you hear me?
Yes.
Okay. Yeah. Yep.
And then there was a similar question about, does the JMS-F or just SunSpec devices in general, are they drawing many DC watts to perform their function?
Again, these are going to have some circuitry that is just there listening for that keep alive signal. But yeah, far less complex, far less power hungry, I guess I should say. so yeah, they are performing a function. So there is going to be some impact, but we're aiming to have these devices be as simple as possible, to work as little as possible, to have the minimal impact in terms of production and reliability on the system.
And then a new question just came in. Jim Conlon is asking if a Sunny Boy system installed in 2015 can utilize Sunny Portal in the Energy app. I think the short answer is yes, and the long answer is it depends.
No, the answer is yes. The Energy app, again, you are linking this to a specific Sunny Portal account, and if the information is there in the Sunny Portal account, it will be shown on the Energy app. Be aware, if it's just a PV system, you're going to have way less than this graphic on the home screen. You're just going to see the PV production because there's no battery inverter, there's no energy meter probably measuring the net power flow to and from the grid. So there'll be less information, but as long as you download the Energy app and again sign in with your normal Sunny Portal credentials, there is unfortunately a confusing button when you first open the Energy app that says register now. Don't do that. Click the sign in and use your Sunny Portal credentials to sign into the app. And you should see the systems that are linked to that account available in the Energy app. And again, it's the classic Sunny Portal or the NXOS Sunny Portal. The same account can be used to access both of those, or the same login credentials can be used for both of those portals. And so whatever login credentials you are using, the plants in that account will be available on the Energy app. So if you have systems on both portals, all of those systems will show up in the Energy app.
And Mike, it looks like the questions keep coming here.
That's fine. I'm fine to keep talking.
No, I like it too. So Stephen Meyer just asked about the secure power supply feature. I had answered that up at the top of the hour, but basically, for those of you who don't know, the secure power supply is a feature that SMA introduced a while back that provides power during a grid outage without batteries. So the inverter is able to yield up to 2,000 watts at 16 amps and 120 volts during an outage when the sun is shining. However, with the advent of rapid shutdown, the way that the inverter works with the SunSpec signal, it's unable to operate at its maximum potential. And so therefore SMA is kind of shifted away from promoting it for rooftop installations. And we're really only promoting the secure power supply on ground mounts right now. So good question, Stefan.
Yeah,
secure power
and
supply
Tyson, I don't know if
awesome
you mentioned
feature.
it. I didn't really hear it, so I want to clarify. That functionality was only available on the Sunny Boy and not the Core One line. Yeah, yeah.
Thank you. Good clarity there. And then Amos is asking about if there's a way to field test the JMS-F unit if they're suspicious of a failure, volts, resistance, etc. on the output side, either with or without a panel plugged in. And I think that maybe, Mike, you're the best one to answer that one, and perhaps you could include in the context of the
Yeah, no, it's a great question, very common question. I think the AP Smart, the company that makes the two devices in the lower two rows of this chart, they have a standalone testing device. And you can put a battery in it, and it has leads to attach to a device. And so you can send, quote unquote, the dummy SunSpec keep alive signal to the device for exactly for that reason, kind of for testing to make sure the device is working. So while it's not sold by an equivalent device is not sold by Jimpsy, the maker of the JMS-F device, again, it is sending a SunSpec keep alive signal to the device. And so I don't believe there is any reason why it should not work as well with the JMS-F device. A great question and a very common one that we get, and so it's nice to be aware of that that little testing unit.
And there are other ways to try to identify the health of your system, but we're getting a message from altE that it's time to end this session.
Time to close. Yeah, we definitely are happy to continue the conversation in our room in the happy hour session that will start soon.
There you go. Well, Mike, thank you so much. And all the attendees, thank you for your great questions and attention here. And we'll keep the dialogue going in the networking session.
Thanks, everybody. Appreciate it.